Okay, so in this week, we are very glad to have Jonathan Wang from the MIT to give us a talk. And his title is L functions and geometric harmonic analysis on spherical varieties. Okay, so Jonas, please.
Thanks very much for the invitation. So I'll start just with an outline. So mainly just to give context, I'll say like a largely conjectural story about like global integral representations, or how to construct more integral representations of automorphic L functions. And so this will involve some kind of spherical varieties. So I'll say like, well, give just some introduction or definition of what they are and how they fit into the picture. And then so the majority of our results are kind of local in nature. So actually local unramified. So I'll state those. And also, so I should say everything that I'll talk about today is going to be joint work with Yanis Sakellaridis. And so then probably with just a little time left, I'll mention what like the flavor of what I mean by geometric harmonic analysis. So how we use more geometric techniques, and just, I guess I'll be kind of highlighting how this can give us some like new directions to go in. And okay, so kind of because I'm doing geometry, everything is going to be over a function field. So we'll just start off with G as a group, connected split reductive group over a finite field. So the split assumption is not strictly necessary for some other stuff. And okay, so now I'll start kind of this general story about how to get L functions, or conjecturally how they fit in. And so, as I said, I guess K is going to be a global function field. So it's rational functions on some smooth projective curve. And okay, so now, so bracket G would denote the automorphic space. So G of the del is mod G of K. And so I'm just going to point out to start this general pattern that I think people in the audience probably know more about than me. But just to put it into, like, I guess, this framework that I want to talk about. So there's been a lot of study in what's now called the relative Langlands program about these automorphic period integrals. So like they all fit into this pattern where you start with some kind of nice reductive subgroup H inside of G. And then so that means also that bracket H will be inside of bracket G. And now, so if you take some cusp form and then you define this period integral, so just you restrict to bracket H and then you integrate, then these in many cases will be related to special values of L functions. And so actually in this case of H being reductive, the talk will not be so much about that, and like I will not offer so much more on that front because that's been studied a lot. But so I just want to say that kind of what nice kind of means, I guess at least for the purpose of this talk, is that in these cases, if you consider this homogeneous space G mod H, then it's an affine spherical variety. I'll say what spherical means later. And so just something to keep in mind is there's a theorem that says that this homogeneous space is affine if and only if H is reductive. This is just to explain that somehow this reductive case, most of the period, or people who study period integrals, there's the subgroup is reductive, and it has, I'm saying it has something to do with affineness. And so just to put this, I'm going to coax it into some other like weirder shape, but this will be like the more general I guess, formula. So instead of integrating over H, I want to integrate over bracket G, and then so this will be an integral. So this is just some form of manipulation that you don't have to do right now. But so also I'm only going to be actually be talking about everywhere unramified functions. So meaning so G, the maximal compact invariant. And yeah, so then, so the left-hand side will be an integral over something like h of those, g of o. And then, so the right-hand side also, it's something involving just the indicator function for this, the kind of O points of this homogeneous space, but like when is a point in g of the dells inside picked up by this indicator function, it's also exactly when it's actually inside h of a, g of o. Okay, so this is some explanation for this formula, but also you can just take it for granted. But so I just want to say that it has the form where f on g is paired with something that I'll call an x Poincare series. So it's the sum over the rational points of g mod h. So this corresponds to some kind of sum over a lattice. So basically the names x Poincare and x theta, are, since they're both something to do with x, they're synonyms for each other. And so kind of another more geometric way to think about it is if you have some function on x of the dells, then you can do some pull-push process to get a function on the automorphic space. Okay, so this is just to say period integrals fit into this x Poincare series format. I guess I did not say that x is g mod h. But now, so the general expectation, which is conjectured by Sakellaridis, is that so you don't need to start with this reductive case. Like you can start with, let's say, any nice homogeneous variety, but probably it'll be spherical. But then I guess mostly heuristics suggest that in order to get like nice formulas, you want to then choose an affine embedding of g mod h into some affine x. So for example, I guess you always need to start, I guess, in these cases with something already quasi-affine, but then like, you can just take its affine closure, meaning spec of its function coordinate ring. Okay, so now this is where it comes in that previously, like partly because you were both affine and homogeneous, you always had some smooth variety, but now this embedding can have singularities. And so for now, I'll just say like you can imagine that there's some kind of function that's actually supported on x of o that's supposed to pick up singularities, some like, yeah, the singularities of x. More precisely, so if you give x of o some kind of algebra geometric structure, then you can, well, I guess technically now probably you can actually define some IC sheaf on it. And then Grothendieck has this function sheaves dictionary where if you have a sheaf, then you can get an actual function from it by taking trace of Frobenius. And then so now again, now I have something on this IC, which lives on top of this x of a. And now I do the Poincare series. So now the only slight difference is that I make this distinction between g mod h and x itself. But anyways, the expectation is now you define this x period. So it's going to be more complicated because previously this IC thing was just an indicator function, but now it can be more complicated. But nevertheless, so I guess around a decade ago, Sakellaridis conjectured that, or at least, so if it's unramified, then the period squared will be like equal or related to a special value of an L function. And so I'll give more precise details about this. But just to say, this is kind of the big picture is that I guess most cases so far, because like we consider things that are basically smooth or homogeneous, because in these cases, kind of this IC function is easily accessible. But like maybe the more general perspective is you don't need to do that. And so just an example, I guess still X is going to be smooth here, but just an example where like this subgroup H is not reductive is the famous Rankin-Selberg convolution. So, okay, so this says if you have two automorphic or cuspidal automorphic GL2 forms, then this integral on the right-hand side is related to the tensor product of standard, tensor product L function. And okay, so this is a case where previously the last page of the conjecture had something about squared, but there's lots of cases where you don't, like just the period on the nose is related to an L function. But in this cases, you should normalize so that the first Whittaker coefficient is 1. And so just to show or say how this Rankin-Selberg also fits into this picture from the previous page. So here we have this normalized Eisenstein series. And so you can think of it as a function or distribution, not on GL2, but on like GL2 times GL2, so diagonally embedded. So I want to say that instead of integrating over GL2, you think of this again still as an integral over GL2 times GL2. And it will have, okay, so I guess Rankin-Selberg has an S in it, but I'm saying there's always a Mellin transform related to this that'll pick up the S. So I'll just stick to this picture or the kind of analog where you just take S equals 0. But it will have this format where you integrate F1 times F2 over GL2 times GL2. And then so the thing I need to specify is what is this X in this case? So it'll be the space A2, so affine plane times GL2, where one copy of GL2 just acts on GL2 from the right, and then the other copy acts diagonally on the left to both A2 and GL2. And so I guess X is still smooth, but here the open orbit is going to be the punctured plane times GL2. And so this is G mod H, where H is the mirabolic subgroup, subgroup for GL2, but then you diagonally embed it. And so somehow the fact that here we have normalized Eisenstein series is related to the fact that I'm taking, so this is IC for X, so it's still an indicator function, but like because I'm taking the indicator for X and not for the open orbit, well, this, I guess in this case, corresponds to the fact that the normalized Eisenstein series is the one for the right formulas. Okay, so as I said, like basically in all the famous examples, X is smooth, but this, I guess the perspective I want to suggest is that this is not necessarily the case. You don't need this assumption to get L functions. And so kind of when Janus made this conjecture, he had this example of a spherical variety where, so you take n-fold product of GL2s, and then there's an extra GM. Okay, so anyways, and H is this kind of unipotent times GM subgroup. And so then you just take it, this is quasi-affine, and then you take its affine closure. And so I think like as soon as n is bigger than 2, this thing will be singular. And so if you look at this, but you can still do this Poincare series construction. And so for n equals 2, this gives Rankin-Selberg, as I sort of described before. And then, so it doesn't like immediately give the kind of known construction for the threefold tensor product, but Anna showed you you can do something to relate it to this construction of Garrett that uses the Eisenstein series for Siegel parabolic. But so the kind of this pattern or this construction of X works for any n. And so in general, this going from period to L function, or like it's something global, and like there are cases where this is hard, which like I'm not going to say anything about, but there are cases, for example, this one where it unfolds by some series of Fourier transforms. So basically, like this relation between period and L function turns into a relation, some local computation. And so since what we do is a local computation, but in these cases where kind of global to local is easy, our results do imply that at least over a function field, this construction of exponent crater series will give you an integral representation of, in this case, the n-fold tensor product. And so this is something over function fields, but like by this Rosetta Stone analogy, like this should indicate that you should still be able to do some construction, some analogous construction over a number of fields to also get an integral representation. Although of course there will be more technicalities and like things to do at the Archimedean place. Okay, so this is kind of the global or automorphic motivation for what's going on. And I guess I should ask, are there any questions?
Yeah, so maybe Jonathan, like, could I just clarify? So for this theorem, n is arbitrary, right?
Yeah.
I see. And I guess in the function field case, this L function is, I mean, when real part of S is very big, is given by a rational function in Q to the minus S.
Yeah.
I see. So, okay.
So yeah, we haven't checked it, but so I want to say that kind of it's okay as long as real part of S is greater than 1, which would be like, I think it might say something new for Moss forms. But yeah, I guess like, so yeah, because they're rational functions, somehow like over a function field, there's like analytically, there's not so much going on. So it like the interest would more be in if this could kind of lead to something over a number of fields. Okay. Okay, so now I'll get a little more specific to say, so nice for this talk will mean that I want my variety to be what's called spherical. And so this is just something really defined over the algebraic closure. So if it's over a finite field, then you just base change to the algebraic closure, and then you require that, so it's a normal algebraic variety, and then it has an open dense orbit for some Borel subgroup inside of G. Okay, so this is the shortest definition, but it's actually also like the least helpful one. And so there's like a bunch of equivalent definitions, and really this condition gives you a bunch of finiteness properties and also connects to good combinatorics. So mostly, it's more that spherical ones are kind of the ones where I guess we as humans can sort of access and do computations with. And so finiteness, for the purpose of this talk, for example, means something like, so if F is a local field, you want finite multiplicities. Inside this as a G of F representation. And so some examples, so toric varieties, just if you take the same definition, but you only allowed G to be a torus, then they were studied like much earlier. And so these are classified basically using some rational cones and fans. So that's kind of this part of the flavor of how spherical varieties are also classified. And then there's symmetric spaces are all spherical varieties. And so these pop up everywhere in number theory and representation theory. And so a particular case is if you, of a symmetric space is if you take X to be a reductive group, but I'll call it G prime because now the big group G that I want acting is 2 copies G prime times G prime, multiplying on the left and the right. And so usual Lagrange can be viewed as studying like harmonic analysis related to this symmetric space. And then so another case of possible interest is if you consider a reductive monoid, so meaning X contains this group case I just mentioned, G prime, but now it can be bigger. And so this is of interest because, so for example, the Godemont-Jacquet construction is an example of a reductive monoid. And so like these approaches of Braverman, Kajdan, and Go to try to generalize Godemont-Jacquet like use this reductive monoid construction. Okay, so now I'm going to give a more, slightly more detailed, but still very undetailed version of what Sakellaridis and then with Venkatesh conjecture. And so since I'm talking here, I just want to say that for like a short but very informative overview of their conjecture, the paper of Witek and Chalet-Wan, the introduction has a very good summary of the Sakellaridis-Venkatesh conjecture. Okay, and so I'll also take some liberties here because like they don't actually say it in this generality, and I'll gloss over lots of details. So again, for an affine spherical variety, X, and a cuspidal automorphic representation, pi, so roughly, if you take this X period and evaluate it on this automorphic form, then if it's not 0, then it'll almost lift by functoriality to an automorphic representation, but for a possibly different group, G sub X. And so this is going to be controlled by a map of dual groups from G check X to G check. So mainly, this is what I wanted to highlight is that like, from this homogeneous space, you can pick up some possibly other group. And so this is important for studying functoriality. And then the second part is then, so there will be a representation of the dual group for this G sub X. And so the square of the period should be related to a special value or so of an L function. But so everything here is for this G check X. Okay, and then so these are some known like rational factors. And so the main point is the existence of some particular rho sub X. And so I'm actually not going to talk so much about G check X in this talk, but I just wanted to say that, so at least in most cases, like, I mean, the conjecture is wide open, but the construction of what to expect for this dual group is mostly known. So due to work of Gates-Curry and Nadler in a more geometric setting, and then Sakellaridis and Venkatesh and Knopf-Schauke define it just using this combinatorial data attached to spherical varieties. But so I would want to say that whereas this rho X, it's conjectured to exist, but it's very much like mostly known only from the perspective of the explicit examples where this has been studied. And so this will be more the focus of my talk because part of our work is to at least give some recipe for how to get this particular representation. Okay, but so I should say, like, how can I like study this thing without going into G check X. I'll just say that later I'll actually only study the cases where G check X is equal to G check. But I'll give some like explicit explanation of what that means. Okay, but so now maybe just to orient people, I'm going to give a list of famous examples in number theory of what kind of G check, well, actually, yeah. So first in this case, I already said the group case corresponds to usual Langlands. And I just want to point out, so as you expect, the dual group is just the Langlands dual group, but for G prime. But whereas, so because the group acting is big, or G prime times G prime, this is a case where like this spherical dual group is not equal to the Langlands dual group of the group acting. And so what I want to say is that that actually makes the situation a little more complicated from the L function perspective. Okay. And then so it's from various perspectives, like Vx here or rho x is just the adjoint representation. So I guess this also is related to how Whittaker periods are related to adjoint representations. And so a case that doesn't like exactly fall into what I said before, because so this isn't really a space, but what I mean is it doesn't matter so much what the space is, but as long as you know what functions on it are, I just mean, so the usual Whittaker model. And so there's a way to make this or precise. But anyways, the philosophy here is that here the dual group is G check. And so for all of these problems, somehow everything should be normalized with respect to Whittaker. So the representation in this case is just 0, or the point. So there is no like representation. And somehow the L function is measuring how far you're away from, or some difference from compared to Whittaker. And then so the simplest case, I guess, where you can consider for a spherical variety is basically where PGL2 has the split torus embedded, or I'll just embed it like this. And so this corresponds to Hecke's period integral, or which gets the standard L function. So here G check is SL2, and then so when I say T star, I mean the cotangent bundle, but since it's just a representation, it just means a representation and it's dual. And roughly you can think of this as, so the T star corresponds to cases where you don't need to square the period to get an L function. Okay, so yeah, Hecke gives you standard. And then, so I already mentioned the Rankin-Selberg convolution. And so it actually works with, instead of 2, you generalize to n. And it's due to Jacquet, Piatetsky, and Shapiro-Shalaika. And so again, here, G check, it will be GLN times GLN. And then you get T star of the tensor product. Okay, and then so very famous example, Gangros and Prasad is this SO2n plus 1 times SO2n mod SO2n. And so again, I just gave this sample mostly because this is a case where you really do need the period squared. And okay, so again, like this going from global to local is very hard. So I won't offer anything new on that front. But so this talk will be about this local computation. And so what I want to say is, I guess, except for the first Langlands case, in all of these other cases, I gave you examples where G check X is equal to G check. And so for the local unramified calculation that I'll explain, I'll say that somehow from the geometric perspective, actually, so all of these cases, you can kind of reduce to just considering something about the Hecke case. So this G check X equals G check condition makes like all of the cases behave in some way similar to Hecke, where you can get an L function from it. Okay, and then so now I'll give, so this is the assumption that g check x equals g check, but actually I'll need to make, so there's this other technical assumption, which means roughly that we omit cases that look like the space of quadratic forms, so GLN mod ON. And so basically this is because, so in these cases, well, like the dual group isn't really defined, or there's no organized way to say what to expect, and it's also not supposed to be related to L functions. So just say, so workers Jacquet and Mao say that, so this period is supposed to match with something like Whittaker, but for a metaplectic cover of GLN. Okay, and basically there's just right now no like good way to organize what happens in that case, or in all of those situations. But concretely, so just to show that like this phrase isn't such a complicated condition, so really what it translates to is that, so first this variety being spherical means it has an open Borel orbit, which I call exerc. But so I'm saying I want the Borel orbit to actually act simply transitively on this open. And then secondly, so for every simple root alpha, I have a corresponding subminimal parabolic. So that means that if I mod by the radical, it's just going to be PGL2. And so excerpt P alpha just means the open P alpha orbit, which contains the open B orbit. And so this thing will have to be some spherical variety for PGL2. And so there are actually only two of them. And I say that it needs to look like the Hecke case. So this condition is saying that you have X, and then on these opens inside of X, it looks basically like some cover of the Hecke case. And then there's these divisors in the complement that can be more complicated. But I guess we have our geometric arguments say that somehow you can control the divisor in some way and reduce back to this Hecke case. And so results about L functions come from this.
So Jonathan, so you don't allow PGL2 mod U as in a unipotent radical of Borel? That's not one of the
right.
case?
Yeah.
Oh, okay. So you are omitting PGL2 mod NT, the normalizer of torus, and PGL2
right.
mod U?
Right.
Oh, okay.
Yeah, basically, so the spherical varieties for PGL2 are basically this PGL2 mod U case and the PGL2 mod the normalizer of the torus. So this kind of looks like this is the type N root case. And then, well, U, I guess, will lead to the dual group changing. So I also don't want that because I guess mostly just as a simplifying assumption, but also because probably you need to say something more in terms of functoriality. But yeah, so from this perspective, like since I really just wanted to compute some formulas, like this case turns out to be the nicest. Yeah, in some sense, like the most rigid. Okay, so now the Sakellaridis-Venkatesh, they give a generalized Achino-Ikeda conjecture, so generalizing the Achino-Ikeda conjecture in the Gangros-Prasad case, so which is relating this period squared, which is a global thing, to some kind of local computation. And so there's several more conceptual ways to say this local computation. Okay, so since I'm over the equal characteristic case, my local field is this Laurent series field. And then so you can kind of say that locally we're trying to compute some unramified Hecke eigenvector functions on G mod H. and so these are also called spherical functions. So I guess historical note is that, well, they're called spherical functions because they have something to do with cases of spheres. And then spherical varieties are actually named spherical because they're somehow the cases that are ideally suited for computing spherical functions. Okay, and then so the other, like the philosophically most correct way is to say something about unramified Plancherel measures. But so these tend to take a while and use lots of harmonic analysis. So instead, I'll kind of sweep everything under the rug and so it's give the formulation that actually requires, or kind of the bulk of the work of Sakellaridis-Venkatesh, which develops a theory of Bernstein asymptotics. Okay, so basically just to say that I'm going to give like the quickest definition, but not the most correct one. Okay, but so I'm going to fix some base point inside the open B orbit. And then I have, so primarily I will be considering this IC function, but so just some function that's unramified on X. So really it should just be on the open part. And then I'll define this, what I call a radon transform. So by integrating over these generic horocycles, so integrating over some n orbits. And so so this thing will be something on G mod n, but then, so it's unramified, so G mod n mod G of O. And so you can, this, well, it identifies with just T of F mod T of O. So it's something, also you can just think of it as something on a co-weight lattice. And then so roughly speaking, so this local computation, or it's this Ichino-Ikeda conjecture is saying that the global period was related to some Mellin transform of this radon transform, so squared. Okay, I say, so it's not actually equal, there's some intertwining operator in the middle, but anyways, this is local computation that I want to talk about, or that'll give you the L function. And also I should say somehow, we'll see later, but like there's a square here and there's a square here, but their square roots are very different. Okay, so I'll give a slightly more precise version of what they want to say about L functions. So in this case of my assumption about Hecke-like cases, so there's going to exist a symplectic representation. Okay, so before I called this rho X, but I'm just going to stick to just talking about the vector space. But there's some symplectic vector space that's a G-check representation together with a polarization of T-check representations, V plus and the dual, such that the Mellin transform of this radon transform for the IC function, so it looks like half of this ratio of L functions that I mentioned previously. Okay, so I should say, like, this can be said just in terms of some nice formula, or in terms of generating series for the radon transform, but like, that's another formula of it, and it's just more like complicated expressions to look at. But so I'll just say, like, basically, essentially, like, this radon transform gives you, oh, actually, so here there should be 0. But so this will give you half of an L function, where here, so this can be, well, almost thought of as a Satake parameter. And so half means, so V plus is, by this polarization, half of V sub X. And then, so the nilpotent Lie algebra is half of the adjoint representation mod the weight 0 part. And so the weight 0 part just contributes some zeta factors that need to be normalized out anyways. But so this has this format. And okay, so now chi you can really think of as a Satake parameter. So this conjecture, this precise conjecture about radon transform implies, at least in this case, the L function part of this conjecture I previously stated.
So Jonathan, can I quickly ask a question here? So this V chi is a honest representation, not a virtual representation, right?
Yes.
Yeah, I see. And also, I guess by the geometric Satake, I mean, it would correspond to some K equivariant perverse sheaf, right, on the affine Grassmannian. Is that right? Or?
So yeah, it would.
Yeah. So is there a possibility of actually constructing that sheaf, that perverse sheaf, geometrically? Anyway, because here this conjecture is just about existence, right? I didn't tell you, like, is there a natural construction that gives a candidate, say from geometric Langlands?
Yeah. So there is, but somehow it's slightly. Yeah, there's some like details, but maybe like the idea is you have this kind of IC sheaf, and then you can consider all x. Okay, so this is something on x of f. But now, so you can, so x has an action of g, so you can act on it by the kind of all of the Satake, all of the every kind of irreducible representation via Satake, and then so if you consider this kind of over all representations, this gives you some big G check representation, and so roughly, so there's gradings and things, but somehow this is supposed to be the symmetric algebra for this Vx via, again, some kind of Satake.
Okay, thank you.
Okay, so previously this conjecture was, so they also make this conjecture not in this case, but I just wanted to say that the symplectic assumption is only for this case where G check X is equal to G check. And this assumption also is what gives you the central value for the L function. So in other cases, you'll get non-central values. But there is, or at least approximately, a conjecture in those cases that's, I guess, less explicitly stated. But so the cases this was considered in, so previously Sakellaridis considered the case I mentioned before where H is reductive, so it's an affine homogeneous spherical variety. And so without any assumption on the dual group. But so here, because X is smooth, so this is a case where you can use more traditional analysis, since so the IC will just be indicator function. And also, so he gets the formula is for this radon transform essentially, but I don't think it's actually immediate or known that it's like it gets a virtual representation, but I'm not sure it's known in all those cases that it's an actual representation. And also, so like even if H is reductive, for example, in these monoid cases, you still want to consider sometimes affine embeddings, which might be singular. So that's also kind of harder to do at the level of just function or classical analysis. And then so some cases where geometric approaches were considered was, so in this G mod, okay, so I use N, but this is U, so the unipotent radical of the Borel. So in this case, So this is related to principal series. But so G check X is just T check, and then this representation is the nilpotent the algebra. And then so another case where, okay, so in this case, they also don't exactly consider the radon transform, but like at least they identify what the IC sheaf or function is supposed to be. But so they do it in this toric variety case that I mentioned. And so here everything is a torus. And so that means that this representation is just a multi-set of weights. And so I mentioned that toric varieties are classified using some cones. And so if you take the generators of this cone, the lattice points of that cone, that's exactly what the weights are. This is just like the simple case of how combinatorics is related. And then so they also consider this generalization of the Gautam-Monge case with something called an L monoid, so a special kind of reductive monoid. And so I already mentioned, so the group acting is G prime times G prime, and then the dual group is G check prime. And then so they don't actually say like it in this way, but somehow there's some translation where Vx, as I stated it, will be the adjoint representation and then T star of this V lambda, where so the definition of L monoid depends on some choice of co-weight. And so you can somehow it'll come out to some picture like this. But I guess so the slogan or an example or slogan is, I guess, so in the Gautam-Monge case, okay, so this was matrices, then so what you get is actually going to be somehow T star of the Rankin-Selberg case. Okay, so we put it in a slightly weird format. Okay, this is just an example of how to get this weird formula above, because so T star of this thing gives this part, and then T star of GON will give the adjoint representation. Okay, and then so the main, I guess, point is that these previous cases in geometry are considering cases where it doesn't satisfy this condition that I was talking about. So there's more issues with functoriality, but like I guess less like the Hecke case. Okay. And then so what we consider is this, so kind of we allow a singular X, but it can be affine, and then it has this G check X equals G check condition. And then so we show that this radon transform, if you take Mellin transform of it, it'll have this formula, this nice format of the central value of V plus, and then so the bottom has something is just a normalization factor, but so it has this nice format, but like the part that's really of interest is that we want to say this is half of an L function. And so unfortunately, we don't quite get this in all cases, but so what we get is, so we know that we want this to be half of something, so like we'll just put Vx to be this kind of V plus and then V plus dual, and then so we can construct an action of the SL2 triple for any simple root. So this can be, I guess, function theoretically interpreted as some kind of functional equation, because if you have the SL2 actions for everything, then at least you know that the weight spaces are going to be, the dimensions are Weyl group invariant. But there's this issue of multiplicities of the different Weyl orbits, or I guess said another way, you need to show that it's not a virtual representation. Okay, but so this would be a representation if the SL2 triple satisfied the Serre relations. And okay, so we currently don't check this, but I guess, and then so because we don't check this, I'm now going to add a bunch of quantifiers to say some more specifics. But also I'll say that, I guess, so there's this conceptual approach, like related to like my answer to Witek's question about Satake. So like there is like a kind of conceptual way where you can possibly kind of using both our geometric construction and this other one show kind of in a abstract way that kind of these SL2 triples have to act in this compatible way to get a G-check representation. But also, so I guess more computationally, we can reduce to the case where G is just semi-simple rank 2. And then the cases where that satisfies this property of G-check X equals G-check, there's like only like less than 10 of them. So like it doesn't seem super easy, but at least it's like a finite computation. And so I'm pretty confident, or I'm pretty sure I can prove it if G is simply laced. But so most of the complications would come from these other cases. Okay, so this is just all these quantifiers. But so if we is assuming that Vx does satisfy the Serre relation, so it does correspond to this conjectural representation, so then we are able to determine exactly which representation it is. So like a priori, there's still some question of what its highest weights are, but nevertheless, we can tell you exactly what the highest weights are with multiplicities in terms of just combinatorial data associated to the variety X. So this at least gives you, like, starting from X, you know which representation rho X to expect. And then, so from point 1 with this functional equation, so if this conjectural rho X, which we now have recipe for, is minuscule, then these Serre relations would have to hold because there's no issue of multiplicity. And so we also show that in these reductive cases, so if H was reductive, then the representation you get will always be minuscule. So this shows, sort of maybe explains why a lot of the examples have minuscule representation. Okay, and then so now in like the last 5 minutes, I'll just give a little flavor of like how we actually prove this, because it's, I guess, different from the more harmonic analytic techniques. And okay, so this is not strictly necessary, but just I'm going to base change to an algebraic closure, and this part actually will work over the complex numbers. And so this is just X of O, and so you can give this set this algebrogeometric structure, which is called a formal arc space. So like basically, this is some version of considering maps from an arc into your original space X. But I guess an arc over in the complex numbers is really two-dimensional, so it's more like you're mapping like little disks into X. But also you can just think of it as just X of O. But so the main problem, or sort of problem, is that this thing is infinite dimensional. And so all of these, I guess, techniques with perverse sheaves, or just to define the IC sheaf, which allow you to kind of control singularities and have good combinatorics. I guess up to a year ago, they were really defined like only for finite dimensional, or more specifically finite type schemes. But actually, so I think now it seems like this case that we consider, I think, does fall under the situation of this new preprint by Boutier, Karstein, and Warshawski, which is to say, like, they say that it makes sense to define some perverse sheaves on these infinite dimensional guys. But even with that, like, if you want to get a formula, at some point you're going to have to do some kind of finite dimensional calculation. And so for this, you still need to use this Grimberg-Kazan theorem, which is saying that this infinite dimensional thing, you can really model it using finite dimensional varieties. And so even better, so they actually do this in characteristic 0, but then Drinfeld gives a proof in arbitrary characteristic. And so because like he does it like for any variety, not spherical ones, but for these spherical ones that we consider, he actually gives like a very explicit definition of what this model is. So here C will be some curve, and so you define it as kind of this set or space of maps from the curve into so the stack X mod B, so generically landing in the open B orbit. But so what's special is that under my assumption that B acts simply transitively on the open orbit, this thing is just a point. So if most of your points on the curve are mapping to a point, like there's nothing going on, so this is really just a restricted product over X of O, okay, with some generic condition and then mod B of O. And so this was previously considered by Finkelberg and Merkovich in this case of G mod N. And so they call it a Zastava space, and because so Zastava is Croatian for flag, so B is flags. And so as I wrote it above, it still looks like some very infinite dimensional thing because this is some restricted product. But so it turns out miraculously that this Y is an disjoint union, infinite disjoint union, but of finite type schemes. So these things are very nice to work with and very explicit or somewhat explicit. And then so not going into the details, but so further inside of these, we can specify kind of for each co-weight some algebraic variety. And okay, so I guess I'll just say the algebraic variety is a little nicer because it actually sits inside the affine Grassmannian. But anyway, so how we translate the original problem into this geometric one is that under the function Sheaves dictionary, so this radon transform that I talked about, defined as an integral before, so you can compute it so on this t to the lambda, or just on the value corresponding to this particular co-weight, it'll just be computing some cohomology for so the IC of this curly Y, and then you restrict to this subspace. Okay, so since I didn't give you the definitions of this boldface Y, like it's impossible to figure out what's going on here, but just saying that integrals go to cohomology. And then so using a bunch of properties of perverse sheaves, like the decomposition theorem and some other stuff, so you can show that like these kind of geometric considerations are enough to give you this format, firstly, that we wanted, where I guess you can say there's something about looking like an Euler product. And then so moreover, like this analysis will actually tell you like what V plus really is that it's has this, or we just define it as the vector space with the basis corresponding to certain irreducible components of some dimensions that you can spell out just combinatorially. But that has to do with the dimensions that are spelled out by data from X. And then, but so now the last part is that you want to say this is half of some actual representation. And so this is the part where you have to do a bunch of geometry, but then you can somehow reduce from this X to just considering roughly the Hecke case, or at least affine embeddings of the Hecke case. And so there kind of, or so you can explicitly compute what's going on, and also that you want just the standard representation. So like from that, you can kind of build up the rest. Okay, so this is kind of just a very loose picture of what's going on that's kind of using algebraic geometry versus, I guess, integration technique. Okay, so